Now that you're tuning in.
We now join Mr. Goddard's pre-calculus lecture on parametric equations, already in progress.
Sorry, welcome back to our channel.
Hi, welcome to my YouTube channel.
It's called JIP, joining in progress. So we're talking about parametric equations. Our problem is that some physical properties, like 2D motion and other things, have more than one dependent variable. The problem? We only know how to deal with functional relationships that have one independent and one dependent variable. Our independent variable that we use is x, our dependent variable is y. We normally say y equals a function of x, y equals f of x. Or we say y depends on x. Okay? In a parametric situation, or if you have a parametric relationship, you have still one independent variable, but you have two dependent variables. Traditionally, we label the independent variable t, and our two dependent variables are x and y. So we have x depends on t, and y depends on t. And what we're going to be focusing on today is looking at parametric equations, graphing them, converting them back and forth between a parametric and a functional relationship, creating a table, just sort of doing the same sort of standard stuff that we do with functional relationships, but then we're going to be dealing with parametric relationships. Nick, can I have you slide over to that table and just make sure that I'm constantly in frame there on that iPad? Or better yet, the content is. All right, let's do an example, shall we? This kind of looks a little new and scary until you start seeing it, and then you're like, oh, that's no big deal. Make sure you have a calculator. If you don't, please come up and get one. So here's a table and a graph of a parametric equation. So x of t is equal to negative 2t plus 2. And y of t is equal to t minus 3. Notice, x depends on t, and y depends on t.
Oh, I don't like it when you put these because then it confuses me with plus.
I try to make the t kind of have a little bit of a curviness at the end, and my pluses are nice and straight, at least on the end.
Thank you.
I'll try. Now, how do we go about developing a table for this? Well, normally when we would develop a table for our functional relationships with our independent variable, we can just pick whatever the heck we want. We pick x is -3 or -2 or 5 or whatever, and then we would plug it into the formula to figure out how we would get the y value. That's exactly what we're going to do here, only this time we have two of these things which depend on t. So I'm going to have my table on my left-hand column is going to be t, but then here I'm going to have an x column, and then I'll have a y column. My t is completely independent. I can choose whatever I want. I choose -3, and then I choose -2, and then -1, 0, 1, 2, and 3. It's independent, so whatever I want. Then I will take that t value and plug it into this formula up here. So help me out here, class. -2 times -3 plus 2. 8, I agree. And then we'll plug it into our y equation. -3 minus 3. -6. All right. Plugging in -2 for our t value. So -2 times -2 is a +4 plus a 2 is going to give me 6. And then for my y value, it's going to be -2 minus 3. -5. Ladies, I want you to take care of -1 and 0. Gentlemen, take care of 1, 2, and 3. Okay? Go ahead and fill out the rest of the table while I fill out the roll, or the attendance, that is. Ladies, I know you're fast on the calculator there. -1, what are my x and y's? 4, -4, and for 0? I'm noticing a pattern here. Gentlemen, when t is equal to 1, what's my x and y?
0, -2.
Keep this train going. For t equals 2.
-2, -1.
And for t equals 3.
-4, 0.
All right. Now, that's a table. Let's go ahead and graph this. Now, Hannah's thinking to herself, this is not going to be easy. What am I supposed to do with the t? The answer is, just forget about it. Okay? Don't worry about graphing the t. Just graph the x and the y coordinates like you always would. So, x value of 8, 1, 2, 3, 4, 5, 6, 7, 8. Y value of -6, 1, 2, 3, 4, 5, 6. We'll put a dot right there. And we'll go ahead and label it t equals -3. No big deal. Great, so that takes care of this one. Let's try the next one. 6, -5. Equals -2. 4, -4. 1, 2, 3, 4, and then down. 1, 2, 3, 4. That's t equals -1. T equals 0, we have 2, 3. Or sorry, 2, -3 rather. 2, 1, 2. It's kind of interesting. Maybe the dot's a little bit larger to cover up for the inaccuracies of my graphing. 0. Did I skip one? Oh, 2, -3. Well, that one should have been right here. There we go. 0, -2. That's at t equals 1. -2, -1. At t equals 2. And -4, 0. Okay. What does that look like? Except for the fact that I'm kind of not totally to scale. Maybe yours looks better. Doesn't that look like a straight line?
Of course.
Okay, yeah, all right. Well, that's what happens. We don't have a nice grid.
That's really funny.
Okay. It should look like a line. We'll see if we get that. But there's something different about this and a normal y equals mx plus b situation. And that is that we have some extra information. We've got this t value going from -3 to -2 to -1 to 0, 1, 2, 3. We actually have an orientation on this line. Maybe you could think of it almost like a direction when it comes to like vectors. And that is that it's going like in this direction. Okay? So it's not just like a line that just goes back and forth forever and ever in each direction. It actually, it has a direction, it has a, it's going like that. As t is increasing, then we're moving along this path. In fact, parametric equations are normally and most commonly used to describe a path of something. Okay? Now, what if I told you that you could use your calculator for this?
Heck yeah.
Yeah. We can use a calculator to generate a table. We can use a calculator to generate the graph. Let's do that, shall we?
Oh, then you just grab the equation.
Grab a working calculator. Oh, you are already, some of you, if you're lucky, from third period is already in the correct mode. But let's all make sure we know how to do this. We want to change out of func mode and go to par mode.
No.
So hit the mode button and go down to the fourth line and you've got something that says func and par.
Oh.
See? Oh wait, no, it just turned itself off. See if I show you. See what I'm talking about? I don't know if you can see if I can. There you go. We moved it down to. Oh no, I didn't. It reset completely. Go to par. Then when you hit y equals, when we go to y equals, it has all kinds of other stuff. Yeah, we have x1t and y1t. So let's go ahead for x. Let's put in -2. Oh no, but where am I going to hit the t button? That x, x. Technically, that button is known as the independent variable button, because when you're in function mode, it'll show up as an x. When you're in parametric mode, it shows up as a t. When you're in polar mode, it shows up as a theta. And when you're in sequential mode, it shows up as an n, which corresponds to all those, and why it's not just a big X right there. So yeah, now you know. So -2t plus 2, hit enter, and then t minus 3. Now, let's go ahead and let's do a zoom standard. So hit zoom, and then go all the way to hit zoom standard, and show me the graph.
Oh, interesting.
That's what I want to see.
It's cut.
Calculator, cheers. All right. Cheers. Zoom standard. Calculator, cheers. Good job. I see it. Hello.
Did you change your message?
This is what it looks like. Okay. She's got it.
Cheers.
Calculator, cheers. Zoom standard.
What are we doing?
Oh, she's stuck it. All right. Now wait a second. Does yours? It looks like walking around. It looked like this, right? Anybody have any idea why the calculator's not showing us all that other stuff over there?
It's not
It's
there.
not there. It's not supposed to.
It's.
We had it. Why is the calculator not showing it, Jeremy? There's something special about those values that it's not showing. They are negative. What's negative?
T.
The t values were negative. When you do a zoom standard, it's going to start off at t equals 0 and count upwards. Okay? What if we want to show some negative t values? Okay, well, we need to change our window settings. So go to where, on the window where it says t, actually we want, window. I'm going to, it says t min, t max, t step. What do we want, if we want to look like our graph that we had a minute ago, what do we want our t min to equal?
-3.
-3. Our t maximum, I'm going to make it 10.
Why is mine at 3?
T step is how many values do we want to calculate? In between each one of these. In ours, our t step was the difference between each one of these. It was 1.
Oh, so should we put it in one?
No, because then it's only going to put a dot and a dot and a dot and a dot. I wanted to put a bunch of little dots. I wanted to go.
Okay.
I might make it 0.1, so it does -2.9, -2.8, -2.7, -2.6. So I make my t step 0.1.
Mine's very straight.
And when it graphs it,
Sure.
doesn't it actually go like this? Did it start on the right, Nick, and move to the left? You didn't see my do-roof thing, so I'm going to do it again. Did it not start over here, Nick, and go? Yeah. Now, every other time you've ever graphed on the calculator, hasn't it always started on the left and moved to the right? So it's really nice that our calculator is actually plotting those points in real time and actually showing us the orientation of that. Okay? Hooray, there's the graph. And we kind of were able to figure out the orientation. Let's go to the table. And true to form. Wow, there we have it. So we don't even need to plug those numbers in when it comes to our homework. We can just, if we have a graphing calculator, plug this in and plug that in, right?
That's what I'm talking about.
Okay, that's pretty nice. Now, here's another thing that we need to know how to do. It would be nice to be able to convert these parametric equations into just a good old-fashioned y equals mx plus b. Okay, so I can figure out the slope, I can figure out the y-intercept. That's what I'm going to show you how to do now. How to do that conversion. How to go from parametric over there to functional. So I'm just going to use those same two equations. X equals negative 2t plus 2 and y equals t minus 3. Step 1, solve the x equation for t. So I'm going to subtract 2 from both sides. So x minus 2 equals negative 2t. Then divide both sides by negative 2. So t equals x minus 2 divided by negative 2. I might do a slight modification because I know where we're going with all this. Instead of dividing by negative 2, I might multiply it by negative 1/2. And it'll look different for every time we do, but that's kind of helpful. All right, step number 2, substitute that into the y equation. That is, I'm going to take this negative 1/2 x minus 2, and I'm going to substitute it into the y equals. So y equals, instead of saying t, I'm going to say negative 1/2 x minus 2 minus 3. So that's y equals negative 1/2 x, and negative 1/2 times a negative 2 is a plus 1, I think. Negative times negative is positive, 1/2 times 2 is 1, yep. Minus 3. So we have a y equals negative 1/2 x minus 2. Does this y equals mx plus b equation match what we're seeing over there with the graph? Jean says yes. Why, Jean? Why does this right here kind of match what we're looking at over there?
This is the same.
Okay, what aspects of it are the same?
The line, but it's not going from bottom to top. It's going from down. So this is negative.
It really just depends on the way that you read it. Okay, talk to me maybe about the slope. Slope of negative 1/2. Does that look like the slope of negative 1/2? Well, it's definitely negative, but it looks like we go down 1 over 2, down 1 over 2. That's what we saw. Now we were here. What does this minus 2 correspond to in a graph? The y-intercept. And is the y-intercept negative 2? Yeah, it is. In fact, we can even see that coordinate right there. So hopefully that's enough to prove to you, yeah, this is the process. You take the x value, or the x equation, solve it for t, and then just substitute that into the y equation, and boom, all of a sudden you've got a functional relationship. Y equals something as a function of x. Sound good? I think that's pretty good. One more problem type that I want to show you, and that's when you've got some quadratic relationships going on. Okay? So Two situation, x equals negative t squared plus 5, and y equals t minus 2. All right, so let's go ahead and do Mr. Goddard's 1-2 step here. So step number 1, solve the x equation for t. So I'll subtract 5 from both sides. I'll divide both sides by negative, so negative x plus 5 equals t squared. Take the square root. Now something weird happens when you take the square root of both sides. Anybody remember what happens when you take square root of both sides? You got to do that plus or minus thing, right? So you get t equals plus or minus the square root of negative x plus 5. And I'm looking at that. I don't know if I like that very much because which one am I supposed to plug in for the t, the plus or the minus? You know what I mean? Now we could go through there and the answer is you have to plug in both of them and you get 2 equations. But at this point right here, like, I don't know if I like that very much. Okay? Because that's giving me two equations. Let me show you an alternate way of doing this, okay? It's okay to leave it as the x. And, the alternate way is just to go the other way around. Take the y equation and solve for t. So y plus 2 equals t. And then substitute this value into the x equation. So we have x equals negative y plus 2 squared plus 5. Now, I don't know if y'all saw anything that looks like this, but anybody, maybe in Algebra 2, seen equations where you have the x equals rather than a y equals? Anybody remember seeing that? You remember what it looks like? Probably not. I wouldn't expect you to completely. Tell you what, let's just go to the calculator. All right, forget this algebra side. Just type that in the calculator. Type in x equals negative t squared plus 5 and y equals t minus 2. I don't know why we're even bothering with the formulas here. Negative x squared, negative t squared, plus 5, and t minus 2. What? That's what I get. That's what I get, Haley. Yeah. Do a zoom standard on that. John, what do you get there? Nick? Hit the graph button. Do a zoom standard. Hit a y equals. Now hit graph. Go to zoom, or go to window. Go to negative 3 to 10. Here? Yeah, negative, yeah, make it negative 3 to 10, but with a step of 0.1. Yeah, now hit graph. There we go. This is what it looks like, camera. Everybody got a sideways parabola? You need to change your window, your zoom. If you didn't, you need to change your from negative, your T minimum negative 3 to T maximum 10, so it's still like 0.1.
What do you need to do?
See, yours is starting at 0 and going to 360 and counting up by 7.5s. Mine's going from like -3 to 10, up by 0.1s. There we go. Share that. Okay. So question, class. What happens if you have an x equals y squared? It's a parabola, but it's sideways. Okay? So I don't know if did y'all ever deal with sideways parabolas? Maybe. It's what happens when you probably, if you dealt with it, it was when you were dealing with inverse functions and stuff like that. Okay? There's something really interesting about sideways parabolas, and that is they are not sideways. They're sideways. They fail the test.
Oh, the line test.
Yeah, they fail the vertical line test.
Oh, yeah.
Which means that it is not a function. But with parametric equations, we have a functional relationship for x and a functional relationship with y, so we can plug values in. Okay? Parametric equations allow you to graph situations and graphs, so to speak, paths or whatever, that are not functional. Okay? That don't have a 1y for each x sort of situation. You know what? That's good, because sometimes life isn't functional. All right? Sometimes sometimes you have motion, you have paths, you have situations that you're trying to model that are not a strictly functional relationship. You might have something that is moving in a path that looks, it starts here and then goes here and then comes back around. Maybe it's going some sort of like outward spiral type situation, okay? Or maybe it's just traveling in a circle, okay? But in a direction, like it's traveling like that. Y equals f of x cannot help you in that. It cannot model that. You're limited by the tools. But if we expand our tool set to include parametric equations, then now we can graph and plot and make predictions about where something is going to be in the future based on the time. We can say, well, where's it going to be when time equals 50? Where's it going to be when time equals 100? Where's it going to? We couldn't do that if it was y equals f of x. Does that make sense? Can you all kind of see the advantage of parametric equations? By the way, programmers, parametric as in parameters. Okay, so you've got a parameter. X depends on t. Y depends on, so it's like your parameter set. Okay. I can't even speak. The application that we're going to examine all of this tomorrow there it is. What? Back to me. You don't want to catch the ball.
Oh, wait, try again.
I
tried to catch it with one hand.
Oh, you got it. All right. Is in projectile motion. All right? Where you have an object, okay, who his x position depends on time, and his y position also depends on time. In fact, the x position depends on the velocity in the x position of the initial velocity vector, okay? And its y position, how high up or how far down it is, depends on the y component of its initial velocity combined with the acceleration due to gravity, okay? And so, at any given time, I could say this guy right here is the x position is a function of time, and his y position is a function of time. I could plug in 3 seconds, and I can figure out how far he is on the x, and I can figure out how far he is on the y, and that's going to tell me right where he is. And I can plug in 10 seconds, and that'll tell me how far he is on the x and how far he is on the y, and that'll tell me his x and y coordinate. Okay? And we're going to be able to do all kinds of stuff with that. We're going to be able to find out when is he going to be at the highest, when is he going to come back and hit the ground, what position is he going to be at, and we can even use the calculator to simulate the path of a angry bird. Okay? All right. So that's parametric equations. We looked at graphing them. We looked at tabling them. We looked at all this other stuff. Let me pass out to you what the homework looks like. We're just going to look at the problems, and you'll say, I know how to do that, I know how to do that, I know how to do that, and then we're not going to really mess with solving any of these. Because you'd rather work on this. Want you guys to share that one? There's one for you. I ran out, I guess. Yeah, can you hand that one back to Robbie? I ran out there, but it doesn't really matter. Let's look at that first problem set. Look at problem number 1. Okay? Nick, you can go ahead and turn off the video there.